Imagine you're piloting a $30 million jet, traveling at nearly 200 miles per hour, and the only runway you have is the length of roughly 2 football fields, floating on the ocean. No second chances, no extra room, just the sea on every side and a wall of metal in front of you. Now here's what nobody tells you about that runway. It doesn't go straight, it curves upward at the bow. And if you're landing, you're not even touching down on the center line of the ship. You're hitting a runway that's deliberately tilted to the side, like someone bent the entire deck out of alignment on purpose. Most people see an aircraft carrier and think, wow, big ship. But the moment you start asking why it looks the way it does, you fall into one of the most fascinating engineering rabbit holes in modern history. Because every single curve, every angle, every degree of tilt on that flight deck, it's not an accident. It's the difference between life and death, between a successful mission and a catastrophic fireball. And the story of how engineers figured this out? It starts with a disaster. Before the 1950s, aircraft carrier flight decks were completely straight, simple, clean. One long runway going from the back of the ship and the stern all the way to the front, the bow, seemed logical. Planes land from behind, roll forward, stop, done. Except it wasn't done. Not even close. Here's what actually happened. As navies started operating faster, heavier jet aircraft after World War II, the old system started killing people at an alarming rate. When a jet came in for landing, it needed to catch a wire. A thick steel cable stretched across the deck, called an arresting wire. That wire would grab the plane's tailhook and yank it to a stop in just a couple of seconds. Physics working overtime. But sometimes the pilot missed. Maybe the approach angle was off. Maybe the hook didn't catch. Whatever the reason, then the plane skipped over every single wire and kept going. Full speed, straight into the barrier nets. Or worse, straight into the other aircraft that were parked at the front of the deck, waiting for their next mission. We're talking massive explosions, fires that could sink a ship, pilots and deck crew dying in seconds. This was called a bolter, and in the straight deck era, a bolter wasn't just embarrassing, it was potentially catastrophic, because there was nowhere for that plane to go except forward, into chaos. The British Royal Navy looked at this problem in the early 1950s, and one man in particular, a naval officer named Dennis Campbell, had an idea so simple it almost sounds too obvious. What if you just tilted the landing area, not the whole ship, not a separate runway, just rotate the landing strip a few degrees off the center line of the vessel, angle it toward the port, the left side. So instead of landing straight toward the bow, incoming aircraft land at an angle, pointing slightly out over the open water on the left side of the ship. Why does that change everything? Think of it this way. Imagine you're rolling a ball down a hallway that ends in a wall. If you miss the catch, the ball hits the wall. Now imagine that same hallway, but slightly rotated, so it opens into a doorway instead of a wall. Miss the catch? The ball rolls out the door. No collision, no disaster. That's exactly what the angled deck does. If a pilot misses the arresting wire and the plane keeps going, called a bolter, instead of slamming into parked aircraft at the front of the ship, the angled deck points that jet out over open water. The pilot hits full throttle, the plane lifts off the angled deck's edge, climbs back into the sky, and goes around for another attempt. Nobody dies, no multi-million-dollar aircraft destroyed, no fire on the deck. The U.S. Navy tested this concept on a carrier called USS Antietam in 1952. The results were so dramatically positive that within just a few years, every major carrier in the Western world had adopted it. An angle of roughly 8 to 10 degrees off the ship's center line, a number that sounds small, but in practice it completely transformed carrier aviation safety. But here's the second thing that angled deck unlocked, and this one is huge. Before this innovation, you could either be landing planes or launching planes, not both at the same time. Because the landing zone and the launch zone were on the same straight line, you'd have to clear the deck, park everything, set up for the next operation. It slowed everything down enormously. In a combat situation, that delay could cost you the battle. The angled deck physically separates the landing operation from the launch operation. The catapults that shoot aircraft off the ship are at the bow, the straight front end. The landing strip is the angled section to the left. Two completely different paths, two completely different operations, simultaneously. A carrier can be landing one jet while launching another, right at the same time, without the two ever getting in each other's way. In military terms, this is called sortie generation, how fast you can get planes in the air, recover them, rearm them, refuel them, and get them back up again. The angled deck basically doubled that capability overnight. It turned aircraft carriers from vulnerable, slow-cycling platforms into the rapid response powerhouses they are today. Now here's where the story gets even more interesting. Because while Western navies, American, British, French, went down the angled deck path combined with catapult launches, another group of nations went in a completely different direction, and they solved a completely different problem by literally bending the front of the flight deck upward. This is the ski jump ramp. And when you first see it, you might think it looks like someone made a construction mistake. The front of the deck just curves up, like a skateboard ramp. On carriers operated by Britain, India, China, Russia, that curved bow is impossible to miss. It looks almost cartoonish compared to the flat American decks. but it is, arguably, one of the most elegant pieces of engineering in naval history. Here's the problem it solves. Aircraft need lift to fly. Lift comes from speed, specifically air moving over the wings fast enough to generate upward pressure. On land, a runway can be 3 kilometers long. A carrier deck may be 300 meters total, and you're not even using all of it. You need to accelerate a fully loaded combat jet from a dead stop to flying speed in an incredibly short distance. The American solution is the catapult, a massive steam-powered, now electromagnetic on the newest carriers, launching system that physically slings the aircraft down the deck, going from 0 to around 200 kilometers per hour in just 2 seconds. It works brilliantly, but it's complex, it's expensive, it requires enormous infrastructure built into the ship's hull, it's heavy, and it can break. The ski jump ramp is a different philosophy entirely. Instead of giving the aircraft more horizontal speed, you change the direction of the speed it already has. Here's an analogy. Think about a ball rolling along the ground. It has speed but no upward movement, no vertical velocity. Now imagine that ball reaches a ramp. The ramp redirects part of that horizontal speed upward. The ball launches into the air. It doesn't go faster than it was moving before, but now it has upward momentum it didn't have a second ago. That is precisely what the ski jump does to an aircraft. As the jet rolls down the deck under its own engine power and reaches the curved ramp at the bow, the ramp deflects it upward. The plane leaves the deck at an upward angle, typically somewhere between 7 and 12 degrees. It's now climbing, not just going forward. Why does that matter so much? Because lift isn't instantaneous. When an aircraft leaves the deck, it's right at the edge of flying speed, maybe just barely enough to stay airborne. If it leaves horizontally from a flat deck at that moment, it might actually descend slightly before the wings generate enough lift to hold it. Over the ocean, even a small descent is terrifying. You have no margin. But if the aircraft leaves the deck already pointing upward, it has a moment, a precious few seconds, where gravity is working against its upward momentum rather than dragging it down toward the water. It's like throwing a ball upward versus throwing it horizontally. The upward thrown ball doesn't fall for longer. Those extra seconds are exactly what the engines need to build thrust and the wings need to build lift. The aircraft transitions from the ramp to genuine, sustained flight. The genius of the ski jump is that it essentially gives the pilot something for free. Extra time in the air, using nothing more than a shaped piece of metal. No additional engine power required, no complex machinery, just geometry. Just the physics of trajectory. A Royal Navy officer named Douglas Taylor is credited with the key theoretical work on the ski jump in the 1970s. The first operational carrier to use it was HMS Invincible, and once again, what started as a British innovation was soon copied by navies around the world who couldn't afford, or didn't want, catapult systems. Today you'll find ski jump ramps on carriers from the UK, India, Russia, and China. The Indian Navy's carriers use it. China's first 2 carriers, the Liaoning and the Shandong, both have that unmistakable upward curve at the bow. There is a trade-off, though, and it's significant. A ski jump launch is fundamentally different from a catapult launch in one critical way. The aircraft is doing all the work itself. It must have enough engine thrust to accelerate down the deck and go up that ramp under its own power. This limits what kind of aircraft can use it and how heavy they can be. A heavily loaded plane, carrying maximum fuel and maximum weapons, might not have enough thrust-to-weight ratio to make it safely up the ramp and into the air. Catapults don't have that limitation. The catapult does the work, not the aircraft's engine. This is why American carriers can launch heavier aircraft on more varied missions. It's why the F-35C, the carrier variant used by the U.S. Navy, has a larger wing and uses catapults, while the F-35B, the short takeoff version used by the UK and others with ski jumps, has a lift fan and vectored thrust to compensate for the lower launch energy. Neither system is simply better. They represent 2 different philosophies, 2 different sets of priorities, 2 different answers to the same fundamental question. How do you get a fast, heavy, complex machine airborne from a very short runway in the middle of the ocean? One answer says, we'll add energy to the aircraft mechanically. Catapult. The other says, we'll use the energy it already has more efficiently. Ski jump. What's remarkable is how both of these solutions, the angled deck and the ski jump ramp, emerged not from massive defense industry research programs with unlimited budgets, but from individual officers and engineers who looked at a problem, thought sideways, and came up with solutions that seemed almost embarrassingly simple in hindsight. Dennis Campbell drew an angled line on a diagram of a flight deck. Douglas Taylor did the math on what a curved ramp would do to a jet's trajectory. These weren't billion-dollar breakthroughs. They were geometry. They were physics. They were someone willing to ask, what if we changed the shape? And that, when you think about it, is the real story of aircraft carrier design. It's not about the reactors or the radar systems or the jet engines, though all of those are extraordinary in their own right. It's about the shape of the deck itself, the angles, the curves, the deliberate geometry of a surface that has to do the impossible every single day. Every time you see a carrier launch its aircraft, that moment when the jet hits the ramp and tilts upward, clawing its way into the sky, you're watching the result of decades of hard lessons, fatal accidents, and brilliant lateral thinking. The curve isn't decoration, it isn't a design quirk, it's the solution to a problem that once killed people regularly, solved with nothing but a change in angle. Now here's the part that should really stay with you. The angled deck, this invention that fundamentally transformed naval aviation and has been copied by every major carrier operating navy on Earth. The US Navy initially resisted it. When the British first proposed the concept, American naval officials were skeptical. It seemed counterintuitive. Why would you deliberately land at an angle to your ship's center line? But the math didn't lie. The physics was undeniable. And after USS Antietam's trials proved it worked, the world's most powerful navy quietly adopted a British idea and built it into every carrier they've constructed since. The ocean is unforgiving. The carrier flight deck is the most dangerous workplace on the planet, or it used to be, before a few curved lines changed everything. Sometimes the most revolutionary thing an engineer can do isn't build something more powerful, it's just bend something at the right angle,